Let's talk a little bit about how to create a navigation mesh system or a pathfinding system that uses navigation meshes. So let's talk about our end goal. The end goal that we want is, if we have a world that looks like this, what we need to end up with is a few things. One is we need to have navigation meshes that represent the entire space. This would probably look something like this, where we have one blue mesh and one green mesh. Right? In addition to that, we also need the graph data structure that represents the connectivity between these meshes, however that takes place. That would probably be represented or look something similar to this, with just two nodes between them. Right? Now, this allows us the knowledge of how do we navigate from one mesh to another, and it also gives us the knowledge of how can we move around within the individual meshes or within these individual rooms, right? This is sort of our ultimate goal of where we want to get to, right? Before this, we need to somehow get from our initial content or our initial level, which looked something like this, where a level designer sat down and built two rooms with walls and floors, or however it is that they design their level. We need to get to this final stage here so that as our game is running, we have all of this knowledge within our new system that we're going to be building. So the first step is building levels. And building a level might mean that our levels are comprised of walls or floors or other 3D meshes, whatever that means, right? Once the level is built by our content designers or by you or by whoever you're working with on one of these projects, the next thing that we need to do, or the first thing we need to do for building the system, is generate polygons. We need to generate these navigation meshes, right? So step one is generating polygons. These polygons that we're generating are the navigation meshes. So we need to go from an empty level or an empty scene, an empty world that's been built, into something that looks a little more like this, where we've built one green mesh and one blue mesh. Something similar to this. The next thing that we need to do is something called triangulation. Now, a rule of polygons and using navigation meshes is that we need to be able to walk from any position on a single mesh to any other position on a single mesh. If our navigation mesh looks something like this, a nice square, right? We know that we can walk from any position on this mesh to any other position on this mesh, right? If we're standing here, we want to go here, straight line. Here, here, straight line. If you pick any 2 points on this mesh, you can move there in a straight line. If we were to build navigation meshes that look like this, and this represented a single mesh, it breaks this rule of being able to move from one position to another. We cannot move from this position to this position through a straight line, right? This would give us an error. This is what causes AI to move through walls or floors or something else on those lines. So instead of generating a single polygon that looks like this, what we need to do is we need to break this into multiple polygons. So even though our first step, when we're generating our polygons, this may come up with actually something similar to this, where we have a single blue, let me get rid of that there. This may actually generate something similar to this, where we have a single blue polygon, which represents all of the spaces that our AI can walk, right? Similar to this one here. Now it's breaking this rule of being able to walk from any one position to any other position. So our next phase that we need to go through here is something called triangulation. Now, technically, triangulation means that we're breaking up our meshes into triangles. A triangulated version of this mesh here may look something like this. Notice how I'm representing the exact same polygon, except now I'm representing it using 1, 2, 3, 4 different triangles. And these 4 different triangles are these convex meshes, which means that we can move from any position on a triangle to any other position on a triangle. So this works for the rule that we want to abide by for navigation meshes. Triangulation gets us to this point where we can start doing the rest of our logic. So the triangulation phase, this phase here, will take our room that we have, with right now may just be 2 or maybe 1 navigation mesh, and breaks it into multiple polygons, something probably similar to this. There. Now I've broken this 1 polygon into 4 polygons that represent the same space. 1, 2, 3, 4. Right? And remember, this is attempting to get to our ultimate goal of something similar to this, where we have 2 meshes and 1 connection between them. The next step is building our graph data structure on this thing. The graph data structure for something like this, I'm going to erase this final room that I have here just because I'm running out of space. The graph data structure for a room like this would look something like this. Here's our walkable space, just like I have in the last diagram. Here's our 4 polygons that we have inside of it that represent this area. Something like this, 1, 2, 3, 4. And then we have our graph data structure, which now needs to be built based on these polygons and how they're connecting. Here's a polygon, here's a polygon, here's a polygon, here's a polygon. These 2 are connected because they share an edge. These 2 are connected because they share an edge. These 2 are connected because they share an edge. And I believe that's all the connected edges here. This gives us a very strange looking irregular shape, but this is still a valid system that we can do pathfinding over, right? So the third step here was doing our graph generation. Our graph representation. Finally, the final step here, and this is an optional step depending on how ideal you want to make your pathfinding system, but the final step here would be some sort of optimization. Now, this here, optimized, would be essentially going through this process of taking a mesh that's broken up into various small triangles like this and eliminating triangles and turning them into convex polygons. So convex polygons still represent spaces that I can move between. And in this case here, we could eliminate that line that I just got rid of. And we could also eliminate that line that I just got rid of. In which case, our final mesh with polygons could look something like this, which is 2 simplified polygons. Now this cleans up our graph data structure a little bit. Our graph data structure would now be represented just by 2 nodes, similar to this, which would make all of our algorithms when our game is actually running a little bit faster. So the final phase here, if you were going to tackle this, would be optimization of this. This final shape. What am I doing here? Would be optimization of this final shape. In which case it would bring something like this that has 4 polygons and 4 nodes inside of a connected graph into a final shape that only has 2 polygons and 2 nodes in its final connected graph, which could look something like this. There we go. And now we have our final set of data that we need. This was that final phase that we wanted to get to have all of the data needed to be able to properly feed into our navigation mesh system. Now our AI can do logic and reason against this representation of our world.